In the previous video, we looked at the effects of inversion symmetry on Maxwell's equations, and we concluded that that meant that the solutions could be separated into even modes and odd modes. In this video, we're going to have a very similar line of reasoning, but we're just going to do this in a slightly more mathematically formal way, and in a way that's also then easy to generalize to other types of symmetries. Now, in order to do that, we're going to introduce an operator that corresponds to the symmetry that we're interested in. So in case of inversion symmetry, let's call this operator O sub I. And what happens if we take this operator and we operate on a certain field distribution H of R? Well, the result will be that this operator applies the coordinate transformation that is characteristic for that symmetry. So in this case, this will go from the R coordinate system to the minus R coordinate system. Okay. So now what do we want to figure out? We want to figure out a way of using this language of operators to express the fact that our system has a particular symmetry, in this case, inversion symmetry. So one way of expressing this is by comparing two different situations. And the first situation is just where we start from a certain field distribution, that's H of R, and we operate upon that field distribution by the operator expressing the properties and the physics of our system, so the theta operator, and then we end up somewhere else. So that's the regular way of doing things. Now, what we could also do, because we have inversion symmetry in our system, is start from that same point over here, but then apply the symmetry operator to move from the R coordinate system to the minus R coordinate system. Okay, and doing this basically means that we have our O sub I operator that does that for us. And then we do the same thing. We operate with the theta operator. Okay, and then of course, because we want to be able to compare apples to apples and not to some other type of fruit, we want to go back to our original coordinate system, and that we do by applying this OI operator in reverse. Okay. Now, if our system has this particular symmetry, then it doesn't really matter whether we take the direct approach like this, or whether we first flip the coordinates, then apply our theta operator, and then flip back. Because we have this the symmetry here, the system cannot really tell these two coordinate systems apart, so the two results should be equivalent. But again, very important, don't forget to close the loop here and go back to our original situation. Okay, so now what I would like you to do is pause the video and see if you can take this diagram here and express that in a simple formula. So the formula basically should tell us that the two situations that we have are equivalent, and the first situation is just applying the theta operator, and then the right-hand side should say that we apply all of these three operators in sequence. But remember, the way we've defined these operators is that they operate on stuff which is directly to their right. So the first operator that we have, this O sub I operator, operates on what's directly to its right, okay, and that will combine us to give a new function. And then the second operator that we have should then be placed immediately to the left of that. So the second operator, the theta operator, should go here, and the third operator should go there. So we need to order these guys from right to left. The first operator that we operate on is the one at the very right. Okay. So now we have a nice formula expressing that our system has this particular symmetry. Let's play around with this a little bit. Let's multiply everything on left-hand side and right-hand side by the OI operator. And then we have OI theta. And then let's also bring the right-hand side to the left-hand side. So then we have minus theta OI. And that thing should be equal to 0. Now, an expression like this has a certain name. That's called a commutator. So let's define this commutator. between two general operators A and B, and it's expressed like this, with this square bracket thing here. By definition, this is equal to the following expression. It's AB minus BA. Okay. Now, why is this thing called a commutator? Because, of course, there's a relationship between the commutative property of certain operations. Well, you can see that if the commutator is equal to 0, then that basically means that AB is equal to BA. So the order in which you apply the operators doesn't really matter. If you now apply this language of commutators to this expression here that we have involving our symmetry, basically means that the commutator of the symmetry operator and the operator describing the physics and the structure of our system, that thing should be equal to 0. So now we have a very fancy way of saying that a system has a certain symmetry, namely that the operators corresponding to the system and the operator corresponding to the symmetry, that these two operators commute. Okay. What does this bring us? Well, we can start to realize that this commutator by itself is also an operator. It's an operator constructed of smaller operators, but nevertheless still an operator. And just for fun, let's try and take this commutator operator and apply it on a certain function h of r, and then see what happens. So pause the video and expand this formula. All right, let's go. So if we have OI theta, the commutator, and we operate on a certain field, by definition, what this will give us is OI theta h minus theta OI h. Okay. And we know that this thing is equal to 0 if we have symmetry in the system. Now let's rewrite this a little bit and bring this second term here to the left-hand side and the other thing to the right-hand side. So we can write this as theta. Then I'm going to introduce some parentheses here. Theta OI h of r, okay, equal to OI and some parentheses theta of hr. Okay, that's just some straightforward manipulations here. Let's now start to make use of the fact that we're not looking at an arbitrary h of r. No, we're looking at an h of r, which is a solution to Maxwell's equations. And that also means it's a solution to the eigenvalue formulation of Maxwell's equations. So we can write that theta of hr, that this is actually going to be equal to omega squared mu h of r, like so. And since this omega squared mu is just a boring scalar, we can bring it outside of the operator. So we have omega squared mu OI h of r. Okay. Let's now see what we have here. And just for fun, let's also put some parentheses here to make it very clear what we have. If we compare what we have over here, this should be equal to what we have over there. So what does this thing actually tell us now? It tells us that if we take an operator theta and we operate on a certain quantity here in between these brackets, which is OI of h, well, the end result of that operation is that we get the stuff between brackets back, OI of h, but multiplied by a certain scalar omega squared mu. That's, of course, an eigenvalue problem, and moreover, it in essence tells us that also the function OI of h is actually an eigenfunction of our theta operator with exactly the same frequency, with exactly the same eigenvalue omega squared mu. So OI of h is also an eigenfunction with the same eigenvalue. Okay. Let's now start to make the assumption again, just like we did last time, that we're dealing with a situation where there's no degeneracy whatsoever. So pause the video and think about what this actually means. So if we have no degeneracy in the system, that means that for a certain eigenvalue, for a certain frequency omega, that we basically cannot have two different solutions. The way we reconcile this with what we've just written here, namely that OI of H is also an eigenfunction, well, the only way we can reconcile these two statements is saying that OI of H and H, they basically should be the same mode. Now, modes are considered to be the same if they're equal up to a scalar multiple alpha here, because that's just a trivial multiplication. We don't consider modes and 2 times that mode to be fundamentally different. No, that's exactly the same mode. So saying that there's no degeneracy means that these two guys are the same, so that H and OI of H, they are related by this alpha here. Okay, so that's our conclusion. Pause the video, look at that equation, and try to figure out what this equation actually means. So what would be one way of representing this equation just using words rather than symbols? Of course, you've guessed it, what we have up here is again another eigenvalue problem. Namely, it tells us that H here is again an eigenfunction of the operator OI in this case, with a certain eigenvalue, which is H, which is A alpha. So that's very similar to what we had earlier in the previous video for inversion symmetry. So you can play similar games there by doing an inversion operator twice, and then you will be able to figure out that alpha is actually plus or minus 1, giving rise to even or odd modes. But the important conclusion here is that if we have symmetry and there's no degenerate modes, then the solution that we find, h of r, which is an eigenfunction of one operator, the theta operator, will also be automatically an eigenfunction of the symmetry operator, the OI operator. So that's very interesting. These two operators will have joint common eigenfunctions. Of course, what happens in the case where there is actually degeneracy in the system, then things become more complicated, because then, of course, this line of reasoning breaks down completely. But then you can say, and we're not going to prove that here, then you can show that it's possible in this case to construct linear combinations of these functions such that the end result will again be functions that are eigenfunctions both for one operator and for the other operator. So the end conclusion of all of our things we did in this video so far is that if you have a system which has a certain symmetry, that means that the operators involved will commute, and that means that it's possible to construct, so there exists a certain set of joint eigenfunctions between these two operators. Joint eigenfunctions, in this case, this means that we have theta h is equal to omega squared mu of h, and OI of h is equal to alpha h. So again, it's very important to realize that it's possible to construct such joint eigenfunctions in general, and especially if you're dealing with degeneracy. This does not automatically mean that any eigenfunction for one operator is an eigenfunction for the other operator. And again, the great advantage of such an approach is that it's typically much easier to figure out what eigenfunctions we have for a symmetry operator, so that we can apply that knowledge to learn something about the different families that can exist for eigensolutions to the more complicated system operator. So going back to the example of inversion symmetry, just the symmetry alone tells us that we will be able to find even solutions and odd solutions to Maxwell's equations without touching Maxwell at all. And that's, of course, a very important advantage, that we'll be able to draw these conclusions without solving Maxwell's equations directly.